Hi OSLO users, this is our 5th video in the tutorial series on Gaussian beams and the paraxial Gaussian beam analysis tool. So in this one we're going to look at point spread function analysis. The key here is that we need to set things up so that it looks like the light is emanating from a source point that matches the Gaussian beam, and then we also have to tell OSLO that we are tracing or analyzing a Gaussian beam in this case. All of the analysis that OSLO normally uses can be used in this type of setup and get accurate results. So there are 4 pages of instructions. So here's the first one. Here's the second page of instructions. The third page of instructions, and the 4th page of instructions. Now there's a lot of words in our instructions for this. Remember that you can go to the examples section in the optics reference to look at further details, but we're showing a lot of words here just to make sure that you can follow along, because I'm just going to go and execute the steps and explain a little bit as we go along. One of the things we can do, and the purpose of this video, is to show a lot of different examples, cases that we have. Okay, so I tested this out a little bit. Here we have the system set up that in the way that it was initially set up, the catalog lens. And the first step asks us to go and, if you've already got it and trust the numbers are set up for the case that step A in this 5th video specifies, and please go ahead and do it. If you're unsure at all, then make sure you have your lens set up correctly. Go to the paraxial ABCD analysis. Notice here I need to go ahead and set 0.25 millimeters for my waist size, and then my wavefront radius is 0 as expected. That will be putting the beam waist in the specification surface, which here is the object. So now I click on the print beam data here, and these are numbers that we're going to use in setting this up for the point spread function analysis. So I can go ahead and just hit OK. And now what we want to do is we want to set up an object point that is at a location that would have a spherical wavefront emanating from that point that would match the wavefront's radius of curvature at the first surface. So here's the number that we're interested in. And here you can see it's E3. So this is saying that the incident radius is a negative, and then it's about 1573 millimeters. This means that we need a point that's 1573 millimeters before surface 1. So we want to set this surface to be the positive of that, so that it's set at the object point, or at the source point, and then propagates out to surface 1, 1573, and then whatever that changes in terms of the number. So of course this is E3, so here we put minus E3. This just never gets old for me. I just absolutely love the fact that you can just type in spreadsheet cells directly into the program. So there we go. 1573 is that number now, but we haven't told it that we actually need to have a Gaussian beam. So to do that, we go here to the setup, and this again is in the lens spreadsheet editor. So we go here. In a later step, we're going to change this to 3 millimeters. You can also, the entrance beam radius, you can also do it here in the entrance beam radius. I'm just going to go ahead and do that now. We are right now on step 5C. That specification was in another step, but I know we're going to do it, so I just did it there. If you then look, we need to note at the bottom that it asks if we can specify a Gaussian beam. We do want to specify a Gaussian beam, and we want to specify it according to the 1 over E squared spot sizes, and we want to pick the spot sizes that match what it is at surface 1. So here that's A3, and since it's a symmetric beam, we do A3 in both the X and the Y directions. So we've got that entered in, and now we're ready to go. This is everything that we needed for that step. So that was 5C. If we go to 5D, 5D actually tells us I need to go back in here and change this to 41.05. You can just change it to a larger number. This is actually kind of a historical number based on old algorithms that it used to use that is no longer really necessary. But we're effectively changing the aperture divisions to a higher number, and this will give us increased accuracy. So now we can close the spreadsheet. I had closed it prematurely there. Change the 3 millimeters. Well, we already did that in a previous step. Now we can go to evaluate the point spread function, and we want to do a point spread function scan here. We don't need to change any of the values here, and you can see up here in the upper left, it is giving us spot sizes as 1 over e squared points. That's one way to tell us that we are using this for a Gaussian beam. And if we take a look, it's 0.1251, 0.1251, and look at that. It's 0.125 in our paraxial Gaussian beam trace. So these numbers are very similar, and so that is a sign that the point spread function is being set up right. Very, very good check to make on that particular case. So moving on to step G. In step G, we're actually going to evaluate, and here we're going to go to a slightly different function. We're just going to print the point spread function value here. So we're going to print it at the paraxial image plane. And then we're also going to print it at the waist location. So cell D5 gives how far we should focal shift the point spread function to be back at the beam waist, which occurs before we're at the image plane. So now we go to, again, print point spread function value, and the focus shift, we use D5 for this. So D5. And so you can see that number matches the waist distance, and so that means we've got the correct information here. Now, one check we can do is that the ratio of the irradiances for these point spread functions, in other words, if we take this D6 cell and divide by the D7 cell, that should be equal to the square of the waist size divided by the spot size. The waist size and spot size relate to amplitude, and irradiance is square, so we need to square that value. So we can go ahead and do that. I'm actually going to look the cells up, D6, D7, and then we have here C5 and A5. All right, so we've got all of our information. So we start with D6 divided by D7. So D6 divided by D7. That would give us 0.91548. And here we now take C5 and we divide by the other one was A5 because it's in the same row. And to square something, it's this star operator. So we square that and we get 0.913, and if we took the difference, we'd get something like 0.002, whatever. So these numbers are consistent, which is also very expected. This is a point spread function analysis that is actually using algorithms versus the paraxial ray trace. But the numbers are similar, and that is entirely expected. So that was step number H. Now we go to step I. And for step I, we're going to generate a plot like we did in the paraxial image plane, but we now want to actually look at it at the waist position. So we recall that our waist position is at cell D5. We go to evaluate spread function. We plot point spread function scans, and then here we're going to put a focus shift in that's equal to D5. And when we hit OK, what you actually see here is spot sizes now that are 0.1197, 0.1197, and if we take a look, we have 0.119458, some slightly different number, but again, this on the left is the paraxial analysis, and on the right is a calculated sort of phenomenon using OSLO's other routines and capability. So very similar numbers, very, very good. Note the normalization has actually been changed here, but we don't really need to worry about it. And I didn't quite follow the instructions that were laid out, so I'm going to fix that right now. We actually asked to do this in a new graphics window. So if I open graphics window, open 2 is one way to do it, GWO, but it's nice to just do it this way. Open a new graphics window. And we want to actually repeat what we just did. So that was this particular command. So that was that location. And then we can repeat the same analysis, but we now want to do it insert window 1. So I make sure I'm on window 1. We go to evaluate spread function. And then we go to PSF scans. And in this case, we're not focal shifting. And we go back. So now we have the two and we can compare them and see how it's changed and that sort of information. Often when I do the comparisons, I try to make windows very similar size or even the same size. So there we can now compare them. So the last thing we're going to do is we're going to actually assess what happens if you truncate this beam rather than having it pass through where the beam is much smaller than any aperture that could clip it, and we're going to clip it right at the stop in the system. So this is steps J through L. So step J asks us to first open or create a new surface in front of the catalog lens. We are going to want this to be a check surface because we're actually going to want to clip light when we do this. And the size we want to pick is make it equal to the 1/e squared spot size. And that's at this particular surface. So we've got that information right here. It's equal to cell A3. So we set that equal to A3. It gets rid of the solve off of that. It's a check surface. Again, it's important here that it's at the aperture stop when we do this. And then now we're at the stop location, and the result will include diffraction. And so if we go here to evaluate, and again, I'm doing the second window that we open, evaluate, and then point spread function scan. We do it right at the image plane in this case. And now if we look here, the spot sizes are different because we're having some diffraction that's coming into play. The 1/e squared spot size is larger. And if we take and look very closely in here, we're getting energy into side lobes. And this is a ring-like pattern. It's no longer a Gaussian, a pure Gaussian. And one other thing to kind of note about this is that I can use my wheel button and scroll out, is that with respect to the normalizations, OSLO normalizes point spread function to the peak of a perfect point spread function for the same pupil size and focusing distance. And so the same pupil size and focusing distance that we have might change the irradiance normalizations in these different cases that we're looking at. Hope you've enjoyed this tutorial and gotten a lot out of it. OSLO is very powerful when doing some layout information for Gaussian beams.